Hi there. Today I'm going to show you how to train a machine learning model for electromagnetic compatibility. For this, I brought an EMI filter to you, which is from an electric vehicle, which has 300 horsepower. And you see quite a few assembly elements here, magnetic elements and large capacitors, and inside there are even smaller capacitors. And if you want to study the impact of these assembly elements on the filter design, you end up with quite a large design space which you need to investigate. And guess what? Machine learning will be the tool to help you to tackle this problem, and I will show you today how to train such a machine learning model. My name is Hansen, and I work with the Institute of Electronics at Graz University of Technology. As a starter, I brought you a very simple example of a low-pass filter with a parasitic inductance. You see here the low-pass filter. It has an inductance, it has a capacitance, and it has a parasitic inductance, Ls. And we have an input voltage U in and an output voltage U out. And if we look at the transfer function of this filter, it looks approximately like this. So first it's flat, then we have a resonance, LC resonance, then it goes down, and we end up with an impact of the parasitic inductance. Now, if we want to vary all these parameters independently from each other, then we have three-dimensional problems. So how many samples do we need to describe this filter? We have 3 samples for L, then we have 3 independent samples for C, and we have another 3 samples for LS. And if we want to vary all of them systematically, then we end up with a number of 3 to the power of 3 equal to 27 samples. And imagine this is a very fast simulation. It runs like 0.1 seconds. We would need a total of 2.7 seconds to run through all varieties this filter can have. 2.7 seconds is not very much, of course. Now we're having a little more complicated filter. So you see here, this is like a common mode filter with common mode inductances 1, 2, 3, L1, L2, L3, and they have coupling coefficients K1, K2, K3, and we also have common mode capacitors C1, C2, and C3, and the same on the other side. So in total we have 9 dimensions, and if we do the same sampling as before, we would have 3 to the 9 samples, which is 20,000 samplings that we need to investigate. And for a simulation time of 0.1 second, we have a total of half an hour simulation time. Now imagine this filter gets even more complex. For instance, we have 15 dimensions. Then we would have 3 to the 15 samples, which is a total of 14 million samples. And that makes half a year of simulation time for a filter which is even not that complex. So let's talk about sampling schemes. Here you see the so-called full factorial sampling, where you have covered the entire space with equidistant points. And as we saw, this results in quite a large number of points, which is infeasible for a large number of dimensions. So let's do something smarter. Let's cover the space such that for each dimension, the entire space is sampled. And I suggest you something like this. If we just sample on the diagonal, we just have 8 samples instead of 64, and seen from each axis, the entire space is covered with sampled on this side and also on this side. But you will readily see that this blue sampling scheme is not very smart, because there are 2 large portions in the square which are not covered by sampled. So we need an additional condition, and this is a maximum distance between the individual points. In such a sampling scheme you see here, these are the red points. They are also distributed such that in each dimension, the entire length scale is covered by red points for dimension 2 and also for dimension 1. But also the individual points have a pretty large distance among each other. And such a sampling scheme, for instance, a sober sampling scheme, is used for machine learning. Cover a space, high-dimensional space, with as few points as possible, as consistently and as widely spaced as possible. This is the sampling scheme which is used for machine learning. The last aspect for machine learning we need to talk about is spatial correlation. Imagine you observe an unknown function over a parameter x, and this function is very slowly varying. For instance, it looks like this. It's a very slow variation of the observables y that you have over the design variable x. And there could be a second function which is very fastly moving and has a very little correlation between the individual samples. And what machine learning does is basically it investigates this correlation. And there is one particular way of machine learning called Gaussian process regression, which I want to talk about here, which fits a correlation function with two unknown variables, so-called hyperparameters, which measures the correlation between the data. So here we would have a very low correlation, which basically means you have very small parameter of lambda and a small parameter of delta. And here you would have a very rapidly oscillating function, which means that you have a very large value of lambda and a very large value of delta. And once you have found such a correlation function, it's possible to predict any new value of this function based on the correlations that you have found here. And for our EMC design, this would mean that X is a design parameter, so this could be the inductance of a filter or the capacitance or a parasitic inductance, and the observable that you have is the filter attenuation function, so the voltage and the output of your filter. After this very little introduction about machine learning, let's return to our initial filter example. This is the filter. We have an L and C and a parasitic inductance Ls. Now we are not interested in one individual filter. We are interested in many filters. So we span a design space where we vary the inductance from 1 to 100 microhenry, the capacitance between 1 and 10 microfarad, and the parasitic inductance between 2 and 20 nanofarad. So in the end, we have a design parameter vector, which consists of three components, which is L, C, and Ls. We are seeing here the plot of the filter responses. There's the frequency axis and we have the filter attenuation. And now we do not see just one curve, we see many curves because we cover the entire design space. And now we see the impact of correlation. There are areas in this filter response, for instance here, where correlation is very high. Basically here we need only very few samples to train our machine learning model. Also here the correlation is pretty high because the filter response depends only on the parasitic inductance. Here it depends only on the capacitance. But there are also regions in which the correlation is very low. For instance, here many things can happen. The correlation between the samples is very low, and we need many training samples in order to train the models. This is here the case, and also here where we see the resonance shift. And we will later see when we train our machine learning model that the accuracy of the trained model will be particularly low in that region, and it will be pretty perfect in those other regions.
Hi, my name is Julian. I will show you how to train your own machine learning model. For this we use our own open source Python toolkit library. Don't worry, it is not necessary for you to fully understand Gaussian process regression. The library allows you to create the surrogate models in only a few lines of code. You can install it quite easily with the Python package manager pip. Just make sure you're using the correct Python version. I recommend you install it inside a virtual environment. We have simulated an LC filter with a parasitic inductance with LT-Spice. Now that we have installed EtherSurrogate, let's load this dataset. First off, let's visualize the filter response curve, which is why train. This is the filter response curve for one combination of component values. Our training dataset includes 100 of such curves. Here are 9 of them. Now let's look at the input parameters, which are the component values of the filter. They are stored in xtrain. Okay, this data looks a bit messy. We don't want our inductance to inherently have a larger impact than the capacitance, just because its component values are larger. Instead, we want our model to learn the significance. That's why we scale our data to center around 0 and normalize its variance. Luckily, we can use the scikit-learn library to do just that. Don't forget to scale your wide train data as well. This looks much better. Now we can move on to the actual machine learning. For convenience, let's import the following libraries. They should have gotten installed automatically along with EtherSurrogate. Jax is a library used for numerical computing. It allows us to train models in milliseconds. And NumPyro is a library used for probabilistic programming. The core part of Gaussian process regression is its kernel. This is also called a covariance function. It describes a similarity between the data points. The RBF kernel has a length scale hyperparameter, L, which defines how far apart two points can be, while still strongly affecting each other's predictions. D is the dimensionality of our data, in this case our 3 components. Next, we initialize the priors. These are the initial values for the kernel's hyperparameters. Setting these to bad values can make the model fail to fit, so try them out for yourself. Here we set up the actual kernel. With the kernel set up, we can now focus on the model. Thanks to our toolkit, this can be achieved with only a few lines of code. To fit our model to the training data, we can use the trainer class. We can also tinker with the trainer class a bit. Let's change some values around. Which values are appropriate can be found out through trial and error or deeper research into optimizers. To get predictions, we now simply type. Don't forget to rescale the predictions. The only thing left is to plot the predictions. This looks pretty good, but we can do better. Let's exchange our basic RBF kernel with a kriging kernel. Simply replace our own kernel code and train the model with the same settings. If you want to learn more about Gaussian process regression, there are some interesting papers linked below. Now it's your turn. Try our toolkit for yourself. The code I used as well as the documentation is linked in the description. Thank you for watching and subscribe for more electronic videos.
You're the signal in my static hum, a perfect match we've overcome. Wires crossed but we still